To the next talk in the session, it will be presented by Dr. Yoomi Park. She received her PhD from Chungam National University, Republic of Korea in 2010. She is currently a principal researcher at the Supercomputing System Research Section at the Electronics and Telecommunication Research Institute, or called ETRI, in Daejeon, Korea. Research interests include high-performance computing, AI, and distributed parallel computing. So she will be talking about introduction to Supreme K project and beyond. So let's welcome her.
Thank you for inviting me. Okay, good morning, everyone. This is Yoomi Park. I'm working for ETRI. ETRI stands for Electronics and Telecommunications Research Institute. Actually, it's one of the government-funded research institute in South Korea. I'm pleased to be here to introduce the Supreme K project, which was a collaborative project between ETRI and several organizations in South Korea to develop core HPC technologies and prototype system. Thank you again for inviting us to present the project to all of you. Before diving into the project Supreme K, let me explain first the why and how this project came to be in South Korea. Let's take a look at the state of the supercomputer ownership in South Korea 5 years ago. I will show you two diagrams. The left-hand side is available computing time per project. At that time, Korea has only few supercomputers at that time. So look at the available computing times per project. With the South Korea's available computing time per project set to 1, the Germany 2.1 times, and Italy 2.2 times, the US 2.3 times, and China 3.3 times that amount. And right figures shows the Korea's total computational power was significantly lower than that of major countries like US, Japan, China, and EU. At the same time, both industry and scientific community in Korea were demanding more and more HPC resources. Eventually, available HPC resources were not keeping up with the growing HPC demands. So how can we get more and more HPC resources, as many as they needed in both industrial and academia communities? The answer is straightforward too, by purchasing the global supercomputer. So far, South Korea has been acquiring the supercomputer from global vendors. A strategy has proven to be effective. But however, as global competition for acquiring HPC technologies grows, there was an increasing worries about that supply chains become less flexible. Regarding this, there was a consensus among Korean governments and experts that South Korea must have capability to build our own supercomputers. And then the important question remains yet. How can we build a supercomputer from scratch? Can we do this? Can we do this? So as you know, all of you know that the supercomputer is made up of numerous highest specification hardware and software representing at the pinnacle of hardware software integrations. So how can we do this? And how do we do first? In these situations, the Korean government and experts have been striving to secure HPC core technologies in Korea on our own. So they developed an execution strategy that includes infrastructure and system technologies and applications into 3 key pillars, which are being realized through the related R&D project by government. And what should we do to develop the HPC technologies is our own? So actually the critical concept of this initiative was the accelerator technology such as NVIDIA GPU. We try to develop a prototype. Even a prototype, we have to develop an accelerator like GPU. So how can we do this? Actually, the initiative was led our SPRIM-K project with the goal of developing our own accelerator and its optimized software and customized computing node for that. Let's dive into the project SPRIM-K from now on. Initiated by the background, as I mentioned earlier, Project SPRIM-K aims to develop our prototype HPC system, left-hand side, based on the in-house developed HPC accelerator, we call it AB21, and optimized system softwares and customized computing node for the accelerator. It was supported by Ministry of Science and ICT of Korea. The project began July 2020 and continued until this year. The total R&D budget was 46.9 billion, approximately $47 million, I think. The project leader, Dr. Woo Jong-han, is here today with us, sitting over there. Yeah. Actually, before taking this leadership for the project, he was a vice president at SK Hynix, where he worked on the new memory system solutions. Yeah, actually, for clarity, I will call this in-house developed HPC accelerator as AB21 from now on. The initiative initiated by this project is initiated by as a part of the national effort by acquire independently key technologies of our own. So we know that how challenging this project was at the time. So we try to bring together all the capabilities from our countries. So the project is a national grant consortium. On this slide, they are involving 2 government research organizations, including ETRI and KISTI, and 8 academic institutions, and 2 industrial local partners. And from the beginning of the project, we have established R&D strategy as follows. The first, hardware software co-design for AB21. We developed AB21 by exchanging mutual requirements with OpenCL parallel programming, compiler and runtime, and the device drivers. I will explain more detail about AB21 from the next slide. The second, to optimize data movement by sharing data in a shared virtual memory space between AB21 and host CPU. The third, we pursued systematic verification for system integration by providing comprehensive verification environment that includes software simulation, FPGA-based hardware emulator, and silicon virtual prototyping. Fourth, we need to carefully manage the issues and risks since especially multiple organizations were involved in this project. And finally, fifth, to tackle the memory wall issues, we conducted prior research on expanding memory capacity. Hu Young-an from ETRI will discover more detail this afternoon. Now let's take a look at the project progress so far. For the first 3 years, we have focused on designing and validating the AB21 chips with software requirement derived from HPL, particularly BLAS library GEM operations. And the left-hand side, you can see a top view of the chip, AB21 chips after the backend. As far as the backend is the last process manufacture before the manufacturing the chips. Finally, we get the AB21 silicon chips in the half of this year. This chip was manufactured at TSMC 12 nano fab, and we are currently testing them thoroughly. And until this year, we test after the testing the chips, we integrated them into the compute node until this year. To the compute node, we developed to validate AB21's functionality and measure its performance. Designed with an RP of 8 teraflops double precision floating point operation, we have to measure the max performance on the compute node. Our compute node has 2 AB21 chips. Here are the specifications for AB21 chips. The chips are peak performance 8 teraflops for double precision floating point operation and 32 teraflops for single precision floating point operations. Based on ARM cache coherent mesh network 700, the chip integrates PE, dual ARM cores, and parallel processing units, and high performance external interfaces such as DDR5 and PCI Gen 5. I will go into the more details about parallel processing unit in the next slide. And to address the data movement bottleneck issues, also the D-cache and scratchpad memory were supported in the chip. And it contains 1.4 billion gates and approximate 4,900 balls in it. The die size is 26 millimeters by 28 millimeters. Let's move on to the this diagram. This diagram shows the logical configuration of parallel processing unit of AB21, which is responsible for actually parallel matrix operations. The parallel processing unit is composed of 8 JMIS clusters. Let me show you a point. Point option. Okay. Yeah, 8 JMIS. Each 8 JMIS is composed of 8 JMIS cluster. Each JMIS cluster is composed of 8 JMIS along with clock reset power gating and memory management units. And each JMIS is is composed of 4 JAC-M and a block of local memories such as instruction cache, data cache, and scratchpad memories. And each JAC-M is made up of a JAC unit and GEM unit. A JAC unit is a core designing for processing OpenCL kernel program to perform parallel based on RISC-V, 64G, and custom instruction set to especially which implemented to manage GEM units efficiently. A GEM unit actually performs parallel computation on the 16 operators, and which can perform up to each of which can perform up to 2 double precision floating point or 4 single precision floating point operations simultaneously. And now I'm gonna explain the software stack for AB21 in blue box. The most fundamental software stack for AB21 is device driver. And also AB21 adopts OpenCL programming model, which was one of the heterogeneous parallel programming models. So we developed a low-level device driver interface library to support the OpenCL runtime. And we also support the management API to help the application programmers. We also developed a backend compiler and runtime for OpenCL, enabling OpenCL applications to perform parallel operations on AB21 chips. On top of that, the BLAST library and MFPG2 libraries and HPL applications can be executed. And next up is a compute node we call the Silver node. Silver node was developed as 2 separate boards. One is a host board with commodity ARM CPUs. We developed the optimized open source based BMC and BIOS firmware. Host board has DDR4 interfaces and PCI Gen 4 support to PCI Gen 4. And the other is AB21 board. It is an accelerator board. Includes 2 AB21 chips and such high-speed signals. Why? The reason for designing and manufacturing separately within 2 boards, to shorten the project timeline by parallel manufacturing and testing each board. And in order to reduce the system complexity of the system integration by testing each board independently. And the enclosure of this Silver node complies with 19 standard SHASH specification. The height is the Silver node is 3U and includes the air and liquid hybrid cooling system. I hope you will be able to see the Silver node at SC24. Here is what the final system will look like when the project is finished. Left-hand side, you can see the logical view of our cluster system. We plan to configure a single rack scale cluster system with 8 Silver nodes equipped with AB21, 2 storage nodes, and 1 management node connected via InfiniBand for computation and Ethernet for management. And as you can see, the right-hand side, the physical view of our cluster system, it includes the partial two-phase liquid cooling, which was also developed in this project. Now I'm some information to you about the next project of the SPRIM-K by Korean government briefly. This diagram, soon after the SPRIM-K project was launched, Korean government announced a long-term HPC roadmap to acquire our own supercomputer technologies and systems in Korea. They developed the HPC roadmap divided into 3 phases. The first phase in the development of core technologies POC. Actually, SPRIM-K project is in this phase. As in the second phase, development of system POC, and third phase is finally, development of full-scale system. And on this roadmap, the goal is to gradually to apply the deliverables for each phase from the small and medium-sized regional Spokane center to the large-scale national Spokane centers. The ultimate goal of this roadmap is to strengthen the Korea HPC ecosystem, including academia, industry, and research ecosystem. And finally, I'd like to conclude my talk. Through this project, we have gained experience in designing and developing our own accelerator, and it's optimized the system software and customized compute node for the accelerator. So even the project is not finished yet, but I'm not sure the project Spring K is a stepping stone for the building full-scale HPC system by ourselves in Korea in the near future. This is our reality. We are diligently pursuing the big tech companies and countries. So we need to face reality, set our goals, proper strategy, and act decisive action. We know that actions speak louder than words. So I think the time to act is now. Yeah, thank you for your attention.
We have time for a few questions. Yeah, there is an online question. There is one question there. Let me repeat. Korea fabricates many mobile phone chips. Will some of the accelerator technologies also end up on mobile phones?
I think our project manager can answer the question.
For now, I don't see any such activity to move this HPC type of accelerator technology into the mobile domain. But I know there are quite a number of activities going on the mobile the domain, where they want to develop their own say MPU type of accelerator for mobile applications, which is quite different. So those are two different as of now.
Okay. There's another question. Will the AB21 product available in the market?
Well, we are, the government-sponsored research institute. We are not a business. But we transfer all the technology to the industry whenever, and whoever wants this technology. So it depends on the industry. I don't think I'm well equipped to give a clear answer to that one. So.
Okay. Yes, Samir.
Just a quick.
How should U.S. researchers collaborate with your organization? How can we port our tools and technology to your platform?
Well, we are still under, the development. So as Dr. Park presents, we're testing our platform with our first silicon as of now. But it is available. It is open for outside researchers to test their code with this silicon and the platform. But right now, there are only a handful of such platforms with the silicons available right now in the lab. So it's not ready for the public use. But sometime beyond next year, because as I said earlier, we're willing to transfer all the necessary technology to the industry. So I hope that sometime later next year, at least one of the industry may make this technology available for others. Again, so we are not equipped to mass produce and support all the products. We're not a company.
Okay. I think there is one more question here on the online. Will there be Vulkan support on the accelerator?
No, we don't have such plan. I mean, this is a silicon, so we already built our, the silicon with a certain floating point capability there. So we don't plan to support the Vulkan as of now. But, so as Dr. Park presents, we are in the planning phase with the government to, with all the learnings from this POC project, to build the larger scale actual systems. So we are in the planning phase for that one. So we may consider the Vulkan or any other the models moving forward.
Okay.